Okay, so continuing along the same lines, now I'm hoping that in between the transition from the previous video to this one, you had a question as to why. Is there any case in which these R1s are unique, or these RIs, these magnitudes are unique, which is this, and this, or this unique? Is there any circumstance in which that is the case? And it turns out that there is, and it is the case that we've drawn over here. And I made a statement of this on the next page, which says that if n1, n2, and n3 hat, the three unit vectors, are in the same plane, which they are in this figure. If you look at it, n1, n2, and n3 are all in the plane of the paper, not pointing outwards or anything like that, then the magnitudes of those vectors are unique. There's only a unique combination that can lead to that vector r when they're in the same plane, right? So there's some, which means that there is some predefinition of n1, n2, and n3. All right. So continuing with that. In such case, the vectors n1 hat, n2 hat, and n3 hat are said to form a basis. Are said to form a basis. Usually we pick a basis which is 1, 2, 3 or something like that, which has a certain order. So let's make note of that. So let's say that these are separate points. Okay. Usually these bases are picked in a certain way, right? That's what I was talking about. Usually the basis vectors E1, or the basis vectors n1, n2, n3, we haven't been calling them E yet, so let's stick with that. The basis vectors n1, n2, and n3 with hats on them have to satisfy some certain conditions, have to meet certain requirements, or, well, if we're picking them, when we pick the basis, they have to basically meet the following requirements. They are mutually perpendicular, right? They are mutually perpendicular, and they form a right-handed set, right? They form a right-handed set, right? So the first one is fairly straightforward, that they're mutually perpendicular. That means we have three unit vectors that are mutually perpendicular to each other. So you would have 1 and 2 in the plane of the paper, and the third vector pointing out of the plane. And when we say that they're right-handed, that has a certain definition in mathematics. This right-handed set is also called a textual set, and we'll write that down. So when I say right-handed, it has to satisfy the following rule. So E1 crossed into E2 is equal to E3 hat, right? And this is some new set of unit vectors, n1, n2, n3, E1, E2, E3. They're all the same unit. They're all a set of unit vectors that are mutually perpendicular, right? So they must be mutually perpendicular and satisfy the right-hand rule. And also, consequently, you will get the other two cross products as E2 crossed into E3 equals E1 hat, and then E3 hat crossed into E1 hat is equal to E2 hat. Right, so these are the rules for right-hand rules and all of that. So let's look at each of these, or at least one of these again, and then you can look at the others and satisfy yourself. So if this is the unit vector E1 hat, and this is the unit vector E2 hat, if you look at the right-hand rule and start at the vector E1, so if you place the fingers and not the thumb of your hand along this, and then curl this vector in this direction into E2, you'll be left with your thumb pointing out of the screen of the paper, which will tell you that E3 hat is now out of the plane, and it's called a counterclockwise rotation. You can see that we're performing a counterclockwise rotation of E1 into E2. You could do something similar with E3. right? You could take E2 and cross that into E3. So the fingers are now aligned along E2, and then you roll them towards E3, and your thumb is now left pointing in the right hand direction or along E1. And this is all done with your right hand, which is why it's called the right hand rule in the first place. And you can do the same thing for the latter.